Welcome back with another video on TryHackMe.com. This is Zaheen. Today we are doing Microservices Architecture. This is a new room. It is just released yesterday, and it will be the part of, I think, their DevSecOps learning path, which is not yet added to the DevSecOps right now, but we will do it anyway since we have completed the DevSecOps path. So we're gonna add this room into our playlist as well. So we have from task 1 to task 7, and before we do that, let's see what we will learn. Explore the problems associated with building a microservice architecture and how to overcome these to build a secure environment. Okay, it is easy and it will take approximately 45 minutes to complete, so let's get into it. I don't see any practical tasks except the task 6, where I can see the includes a deployable machine. Other than that, I think we are good to go. So let's do that, guys. So introduction. So they pasted Kubernetes laboratories here. All right, no problem. When Kubernetes was first introduced in the intro to Kubernetes, we already covered this room. So I will put a link above here. It was done using the context of the increase in popularity of microservice architecture. That is, instead of having an application built as a single unit, a monolithic architecture, they were separated into containerized microservices. In this room, you will continue your DevSecOps journey by learning about security concerns when working with microservices architecture, how they can be addressed within a Kubernetes cluster. This room will teach you methods of securing a microservices architecture to help Kubernetes laboratories address some concerns they have. So here we have microservices architecture, and what they're trying to depict is so they are applying some kind of, the security hardening on each layer in the Kubernetes. So microservice architecture for the good of all of us. Kubernetes hardening, advanced, DevSecOps, and TryHackMe. Awesome. So I put that in the DevSecOps room, right? Learning prerequisite. First, make sure the basics have been covered by completing the intro to Kubernetes. We already have done this. Then let's check it out. And I'm sure we have done this already. Yeah, we have done this already. Then the two rooms that precede this should be completed. Cluster hardening, we already have covered this. And Kubernetes best security practices. I think that one we did not cover. Okay, cluster hardening, we did not cover. But similar to that, we had covered before, and they are saying that if you would also cover the Kubernetes best practices, that would be awesome. Okay, so what we will do after this video, I will cover these two rooms as well. So for now, let's move forward. If you are unfamiliar with the containers internally, then you should consider doing rooms like Introduction to Containerization and Intro to Docker and Container Hardening. So at least these two rooms I have covered, and I will put the reference up here. Learning objectives. The user will understand pod security standards and pod security admission and depreciation of pod security policies. Okay, the user will understand the problems faced when working with a microservice architecture. Excuse me. The user will understand MTLS and how it can be used to secure communication between microservices. Okay, the user will understand that a service mesh is and how it answers problems associated with the microservices architecture. The user will understand STO service mesh architecture and how it can be used with Kubernetes microservice architecture. Awesome. So for the first one, I mark it as complete. So there are a lot of learning lessons here. Well, let's see how they present the information. So the two Kubernetes laboratories, we have PSS and PSA. Let's kick off this room by clearing up a common point of confusion. One way you can secure a microservice architecture is by ensuring the pod running these microservices have to meet certain security configuration requirements before they are accepted into the system. In the past, this was done by defining PSP, pod security policies. I think this one we have covered it already in our DevSecOps path. You just check it out. The rooms which are related to Kubernetes and pods. This term is a real buzzword in the world of Kubernetes security. If you are curious for this topic, has taken you to read articles or blog posts, then it is likely you will have seen PSP mentioned frequently. What currently is not mentioned frequently is that PSP has since been deprecated as of Kubernetes version 1.21 and removed as of Kubernetes version 1.25, which is I think the latest one. This task aims to first address the depreciation of PSP to clear up any confusion about its absence in these rooms, then define Kubernetes replacement for them. That replacement would be PSS, Pod Security Standards, and PSA, Pod Security Admission. So the PSS is the new standard, and PSA is what we call Pod Security Admission, and these are replacing PSP. All right. Pod security standards. Pod security standards in Kubernetes essentially define 3 levels of security you want to be enforced. These levels of security are rather confusing, rather to as 3 policies in the official Kubernetes documentation. These level policies outline different restrictions for different use cases. Let's take a look at what they are. Privileged, baseline, and restricted. Privileged, as the name suggests, it is the most relaxed policy and is unrestricted, with the wildest level of permissions being granted. Non-privileged escalation are allowed using this policy, but they are intentional. Use case for a policy like this would be a system or infrastructure level workload which is managed by a trusted cluster administrator. Yes. Baseline. The baseline policy is designed for ease of adoption. It is a minimally restrictive policy that prevents non-privileged escalation. A default pod definition would be allowed using this policy. Use case. This policy is for application operators and developers working on non-critical applications. Some applications will need baseline permissions to run a restricted, since the latter would be too well restrictive. So this is to run, for example, non-critical application. If you are doing some kind of development, or know if there is any operator of the application, they can use this baseline. But most ideal is to go with the restrictive. So the restricted, as it sounds, this policy is highly restrictive and follows current pod hardening best practices. However, this does come at a cost of compatibility. Use case. This policy would be used in development and running of security critical applications. So as the name suggests, it is restricted. That means we are already applying the pod hardening best practices to date. Okay, so these are the 3 levels policies which can be enforced. Ensuring pod created follow a predefined standard, so you can rest easy knowing that it is being deployed into your cluster. Only how are these standards enforced? Okay, so pod security admission in Kubernetes best security policies practices room. We covered the 3 stages an API request goes through before being accepted. Persisted. If you remember, the last of these 3 stages is admission controller. Check that are done against a request depending on which ones have been enabled. It was mentioned that the Kubernetes has many built-in admission controllers, and one of which is pod security admission controller. It is this admission controller that enforces the pod security standard outlined in the previous section, and is what is being referred to when we discuss PSA. pod security admission. If a PSS has been set, that is a standard. Okay, standard is a different thing, and admission, the PSA is a different thing. Has been set, for example, against a namespace, then the pod security admission controller will be triggered upon any pod creation requests in this namespace. What the pod security admission controller will do upon a violation of this standard will depend on the mode that has been selected. There are 3 modes: enforce, audit, and warn. So mostly it will be warn, right? And then once we'll fix the issue, then it is enforce, and at the end of the day, somebody will come and audit your cluster, right? So let's go with enforce. If a pod creation request violates the policy, request will be rejected. Audit. If a pod creation request violates the policy, the event will be recorded in the audit log. However, the request will be allowed and the pod will be created. Warn. If a pod creation request violates the policy, a user-facing warning will be triggered. However, the request will be allowed and the pod will be created. So this is a user-facing warning, and this is just event creation in the audit log. And this is how they envision. There is a request, and then you applied the pod security admission here, and it will decide, okay, the pod will be created or pod will not be created. So most of them will create the pod, but in case of enforce, if the request violates the policy, pod will not be created, will never be created. Okay, moving on. PSA and PSS in a Kubernetes cluster. Now we have established how they work. Let's take a look at how we would apply these to our Kubernetes cluster. Let's consider a common use case. We have a non-critical application running in example namespace and want to ensure all pods running in this namespace are protected against non-privileged escalations, denying all pods that do not meet these standards. To enable these pod security standards at a namespace level, we can use labels. Kubernetes defines labels that you can set to determine which of the pre-defined pod security standards you want to use in the namespace and what mode you want to use. Here is the syntax of the label. So we have pod as security.kubernetes.io, and then the mode is equal to and then the level. For example, if you wanted to set a baseline level and have it be enforced, then pod security.kubernetes.io enforce is equal to baseline. An optional label can also be included. If you want to pin the version of the policy being enforced or audited warn to the one included in the Kubernetes minor release or the latest release, this could be done with pod security.kubernetes.io enforce-version is and then the colon and then space v1.30. So this is where we are enforcing that we are going with the baseline, and then we can also create a label for this particular change that we have done. For example, enforce-version is equal to v1.30. So if we change something later on, we can update the labels as well. This is a cool trick. I mean, yeah, that's the format of the label. But how would we apply this label to our example namespace? We can do this by using a kubectl. So you know that the kubectl is the main command line tool which will be used to configure the Kubernetes cluster or deploy new workloads. Note, the dry run option is not essential, but it is best practice as it allows you to check if all running pods in the namespace you are labeling would be admitted with the security standard you are applying. Essentially, you are trying to avoid an instance where an application pod is in this namespace created before labeling restart, but gets denied as it does not meet the newly labeled security standard. If the dry run command returns namespace labeled without any warning, this means that all pods running in this namespace would be admitted using the security standards you are about to apply. The command would then be run without dry run flag to label the namespace. Okay. So for example, if a pod is running in your cluster, okay, and it does not comply with the new policy that we want to apply to our cluster, okay, and it is labeled that it is restarting, okay. Now at the same time we applied our policy, so what will happen is we will try to run it with dry run before to see if everything is, our cluster is in compliance state or not, or if there is any issue. So in this case, once we run the kubelet with the dry run command, because one of the pod is restarting and it is not complying with the new policy that we will put in place, so it will show us an error or a warning. Okay, so in that case, then we need to address the warning and try to run dry run again and see if there is any warning. Once there is no warning, then we can run the command without dry run. So this will actually execute the policy or enforce the policy that we are setting. So the kubectl label -dry-run is equal to server -overwrite ns namespace is example namespace, and then the pod security .kubes kubernetes.io is the namespace that we are using internally, and then the enforce, this is the workload namespace that we are using inside the two Kubernetes, and then we are saying that we want to apply the baseline, okay, which is less restricted but will block non-privileged escalations attacks. Okay, it may still have the day zero or something. One final note on pod security admission. We have just gone through how to ensure a pod security standard is applied and enforced at a namespace level using labels. However, there are some configuration changes that can be made at a cluster level. As mentioned, Kubernetes provides us with the pod security admission controller, which enforces the pod security standards. Okay, so the pod security admission controller will enforce the pod security standard. So this is a distinguish. Okay, one is standard, one is written instruction, the other one is the enforcer, okay, who will take this written instruction and actually enforce it. Okay, you can configure this admission controller on the master node to make custom changes. This includes defaults where mode level is not set and exemption. For example, authenticated user or namespaces, which should be exempted from the pod security admission controller. More on this is available in Kubernetes documentation. So you can still, set some kind of exceptions where, for example, the authenticated user or the namespaces will not be checked, or the mode will not be set for some of the namespaces. All right. Okay. Which pod security standard level would you use to ensure cluster hardening best practices are followed? Best practices. So I will use enforce, of course. Not the just a moment. So standard is restricted. I'll go with restricted. Awesome. Which pod security standard level allows non-privileged escalation? So non-privileged escalation is privileged, right? So here we have allows. The word is allows, okay, not reject. So it is privileged. Which pod security admission mode rejects a request upon policy violation? So it is enforce. We have learned this. Enforce. I'm a big fan of copy pasting, so I'm just copy pasting here instead of typing. What would the syntax of label enforcing a restricted policy look like? Label enforcing. here, restricted policy. So all we need to do is restricted and we are good to go. Awesome. So let's move on to the task 3. A very microservice problem. Okay. 03. Visualizing a microservice architecture. Before we dive into some of the problems that can arise when building out a microservice architecture, let's visualize what we mean by it. As covered in microservice architecture, it involves separating parts of an application into microservices which run as a containerized workloads instead of having a single piece of code known as monolithic architecture. Let's consider a few examples. A streaming company like Netflix, an early adopter of this style of architecture, may choose to split their application into microservices like streaming, recommendation, profiles, catalog, query, etc. An outline storefront such as Amazon may have microservices like web app, basket, order, product query. Here is how the microservices architecture is set up here at Kubernetes Laboratories. Okay. So we have web server, we have test chambers, we have subject registration, we have database in one pod, we have products, and we have results. So all of them are microservices itself, I think, and deployed on different pods. The problem with the microservice architecture: skirting pod to pod communication. You may remember in the cluster hardening room, we discussed how to restrict pod to pod communication using network policies. Now we will discuss how to secure communication between pods. A typical microservices architecture will be set up as follows. A client will connect to Kubernetes cluster using HTTPS, will hit the load balancer, which will then forward the request to the ingress controller, also using HTTPS. Likely there will be a firewall protecting the cluster as well. However, from this point onwards, once we are inside the cluster, the pod to pod communication is done using HTTP, which is way faster than HTTPS or some other insecure protocol. In other words, the cluster itself is protected, but once inside there is insecure unencrypted traffic. That is, to improve the overall performance, right? So this is client trying to interact from his browser using HTTPS. Then some points are missing here. For example, user will enter the DNS address, for example, TryHackMe.com, and then the DNS address will be translated to an IP address, and then the IP address will be either of the load balancer or the firewall or web firewall, and the load balancer comes internal network. Okay, so this load balancer could be either on the Kubernetes load balancer service that we covered already in the intro to Kubernetes or the Kubernetes room. Just check it out in the playlist of DevSecOps. You will get to know that. And then what they are saying, okay, the HTTPS traffic is coming to the load balancer. Load balancer will inspect it. If the load balancer is a WAF, then it will inspect it, re-encrypt it, and send the traffic to the ingress. So the ingress is the service itself within the Kubernetes. Okay. So in this case, either it is passed through. For example, the HTTPS traffic will come to the load balancer, and load balancer will not do anything, or any other appliance will not do anything. No inspection or no introspection. It will just pass through the traffic to the ingress, and now the ingress will basically send the traffic to one of the pods that are running. As you can see here, we have service here, service here. So this service means it's not a load balancer service in Kubernetes. It's a service. For example, the web server is running on this pod. So this is what they meant by service here. And the other one could be, for example, database. Okay, so the web server is communicating to database on HTTPS, which is insecure, which will increase the overall performance of the application. But if one pod is compromised, that means the attacker can have unrestricted access within the cluster itself. So this is the main concern related to the microservice architecture, especially if we are considering it to be deployed on Kubernetes. Okay, so it's Kubernetes mean it will be a Docker or container, and how we will protect the communication between the containers or the services itself. Okay, so this is the main concern. Let's see how we're gonna handle this. This has certain implication for an on-premises network. It would not be following best practices, but the implications are worse when you consider a cloud deployment, which microservice architecture frequently or a cloud service provider provides multiple AZ availability zones. If you know about if you had read about Azure or AWS or GCP, I mean, you would familiar with this concept, the availability zones. To ensure the uptime of your application, if one AZ goes down, availability zone are used to make sure that your application is highly available. Which means, for example, if you deployed your application on 2 servers, so both of them will have different availability zone. For example, if one server is impacted by power surge or there is power shutdown or anything like that, so only this server or rack will be impacted. Other servers which are in an other availability zone are still be working fine. So this is what we meant by availability zone here in a nutshell. If one AZ goes down, another one remains up. That is the main thing to achieve the highly available architecture, right? HA. Before of this, some services in your cluster may be running different AZ, meaning unencrypted communication between services could be intercepted by an eavesdropper. That is true. It's for this reason traffic between services should be encrypted using MTLS. I think this is a different form of TLS, which requires less resources to implement. Okay, so we have availability zone 1 node. This is the node 1 running, and then it is trying to communicate on HTTPS. Availability zone 2, this is node 2, and somebody is trying to see our traffic or intercepting it. MTLS, Mutual Transport Layer Security, provides mutual authentication, ensures that both sides of the communication are authenticated using certificates. Awesome. As you know, when using TLS, transport layer security, a server has a TLS certificate and public-private key pairs. However, the client does not. In TLS, on the other hand, both client and server have a certificate and authentication using a public-private key pair. Another noteworthy difference is that with MTLS, the organization that is implementing this, it acts as its own CA, certificate authority, instead of having an external organization validate its identity. Here is a visualization of how MTLS works and the connection steps that happens between a client and server. These steps highlighted with a star or additional step in the MTLS versus CLS. Okay, awesome. Let's see. Hey, can we connect? Servers, sure. Here is my cert. It will give the public certificate to client. Thanks, let me verify. Looks good. Here is my cert. It will give its public certificate. Server, I have verified. Looks good. I granted you access. Okay. Client, TLS encrypted communication, and server is also communicating the traffic. So that was from DataPad, Kubernetes Laboratories. Okay, a lot to consider. Let's consider this example. Wait. Where is the static? The steps highlighted with a star are additional steps. Okay, so these are additional steps that are highlighted. So in the TLS, we don't use client certificate, okay, because the client is using our public certificate to encrypt the traffic, and once we send the traffic, it will use our public certificate to decrypt the traffic. But in MTLS, both have their own certificates, and as you can see here, they have mentioned in the star that the server is now using the client public certificate to encrypt the traffic for client. Okay, so both of them and certificate using their own kind of private certificate, but once they want to send some traffic, they will use client will use server's public certificate, and server will use client's public certificate. So both of them have their own private certificate to encrypt or decrypt the traffic. A lot to consider. Let's consider this example of microservices architecture. Each of our microservices is running inside of a pod. Each one will have its own business logic, aka functionality. What is its purpose in our application? Then our microservice will talk to each other. For example, one of our employees may connect to the web app service, which will talk to the results service, which will then logged, will communicate with the database DB. For this, each microservice will need to know the endpoint of all microservices it talks to. This is known as communication configuration. Above, we discussed the importance of having pod-to-pod communication and securing using MTLS. For this, the microservice will need to have the security logic included as well. For a microservice to be robust, it will need to include some kind of retry logic, which retries a connection if the microservice it communicates with it is down. For example, if you're familiar with the .NET side of the things, so usually in microservice we use Pulley. So Pulley is a NuGet package, which will basically, if there is a transient error, network level error, it will automatically retry to call the service. Okay. For example, as well as all this, service monitoring is frequently needed to gain business insights into the microservices usage, performance, as well as tracing data, which can be useful in troubleshooting context. Put all of this together, suddenly your microservices is not looking so micro. Yeah. All right. So this is tracing, retry, monitoring, business, communication, and security. So we need to implement all of this in each microservice level. So obviously, I mean, why would I try to create microservices? To make sure that less resources are used and the services are scaled independently of each other. For example, the product query service is used most of the time, and for example, total of 100% traffic, 80% traffic is coming to this service, the product query service. Then you need to scale this product query service only. Rest of the system will just work fine, right? So this is one of the benefits of using the microservices architecture. But as you can see, since responsibility is increasing, so microservice is kind of becoming another monolithic service, right? Okay, so so the load is too much for this container or the pod to handle, and as you can see, it tries its best to serve the number of the tasks that or the responsibility that we put forward on its plate. Okay, and it is also sweating. All of this non-business logic needs to be added to each microservice application, which can lead to developers spending all of their time on these configuration instead of actual application deployment itself. On top of this, the manual configuration of this non-business logic, sometimes across different teams with different dev team assigned to certain microservices, can lead to misconfiguration, which is especially concerning in a security context. This is where service mesh comes in. So for example, if one team is taking care of, if we go back to one service, for example, this is web public web service, which is hosting for example, a TryHackMe site. The other one is hosting a query service or the payment service or something like that. So most of the time, one service is handled by only one team, one separate team, and the other service is handled by another separate team. So because we are deploying our own services and we just take care of our own service, and that's it. We don't have any responsibility to take care of the other service, right? One team. So what could happen is, if we need to implement the MTLS, so we need to make sure that the configuration on the both side of the team are accurate and there is no misconfiguration. And there could be a chance of misconfiguration if there is no communication between the teams which are developing and deploying the services independent of each other. So this is the concern raised by TryHackMe here. All right, let's move on to the questions. A Microsoft architecture is an alternative to what style of architecture? Monolithic. As you know, I'm a big fan of copy pasting. Monolithic. I'm gonna paste in here. Come on, man. Taking a lot of time. All right. The problem with Microservice architecture is that the service-to-service communication is usually unencrypted. Non-encrypted or unencrypted. What is the word that we are looking for? Unencrypted traffic, right? Insecure or unencrypted. So let's see which one is we need to add. Unencrypted. Yay! The solution to the above problem would be to have both sides of connection authenticated using MTLS. Okay, awesome. So we still have 4 tasks to go. So we're gonna wrap up this video. For now, we already in 37 minutes into the video. So thank you guys for joining me on this video. And we're doing on, the very first day of launching this room. So if you have any comments, please let me know. Put it in the comment section down below. If you like this video, please give it a thumbs up. And if you haven't subscribed, please subscribe. Support us, support the channel. It's a very small community right now, so if you can support the channel, that would be appreciated by subscribing to the channel, and also enable the notification so you get to know if I release a new room on this channel. So thank you guys for joining me, and I will see you in the next video where we'll discuss from task 4 to task 7. Thank you.